All right, so for this first problem, we can work on this rational expression to simplify it a little bit. Remember not to drop your limit notation until you have actually used direct substitution. So I'm going to factor these two trinomials, and it's likely that expressions will get canceled out. So here x minus 4 is cancel. So now I can take the limit as x approaches 4 of x minus 1 over x plus 2. And direct substitution will work here. So if I plug 4 into this, I get 3 over 6, and then that reduces to 1/2. If I would have plugged 4 in to begin with, it would have calculated out, I can see it factored, it would have calculated out to 0 over 0, and that's indeterminate. So that means that you have to work on this, simplify it until you get something you can plug in. All right, for number 59, so again, I can't plug in 0 here because I would get 0 divided by 0. That's an indeterminate form. Talk more about that in a little while. So what we need to do is get rid of this complex fraction. So there are a few ways to do it, but we have talked about multiplying by the least common denominator out of all the complex fractions. So that would be 3 times x plus 3. And you can do that on the top and the bottom. Here you're just multiplying by 1, so this is legal. And you can distribute this through. So now this is the limit as x approaches 0 of, so here the x plus 3's would cancel and I'd be left with 3, minus, here the 3's would cancel and I'd be left with the quantity x plus 3. Nothing cancels because there's no fraction in the denominator, so this would just be 3 times x plus 3. And then we distribute the negative. So that's going to be the limit as x approaches 0 of 3 minus x minus 3. So the 3's are going to cancel. You've just got negative x left up there. And then we have 3x times x plus 3 in the denominator. I can simplify a little bit more. This x cancels with this one. I still have a negative up here, like a negative 1. So now when I try direct substitution, it's just negative 1 in the numerator. There's this 3 on the outside. 0 plus 3 is 3. So negative 1/9 is the limit of the original problem. All right. Now, we talked about some properties in our notes. So here, two things. We have a memorized limit. The limit as x approaches 0 of sine x over x is equal to 1. We verified that graphically when we first looked at this. So this little 5 that's out here, that's just a coefficient. You can pull a 1/5 out in front and then keep the limit here. So 1/5 times the limit as x approaches 0 of sine x over x. So these two things are equivalent. You're allowed to pull constants out in front of the limit. So I can take the limit of this expression, which is equal to 1, and then I can multiply it by 1/5. So 1/5 is my solution for that problem. For number 68, I can't plug in 0 because if I do that, I get 1 times 0 divided by 0. So I've got to work on this a little bit. We get to break out our trig identities. So this is the limit as theta approaches 0 of cosine theta. And then I'm going to use the quotient identity to simplify tangent. It's sine theta over cosine theta. We're dividing the whole thing by theta. So these cosines can cancel out. And now I'm back to the limit that we just used in the last problem. The limit as theta approaches 0 of sine theta over theta. Again, that's our memorized limit. It's equal to 1. We did check this graphically. Numerically, this is kind of cool to think of. Sine theta, remember, is the y value of a coordinate. So whatever the y value is when we plug in theta, we're at a certain height. And then if we plug in that same theta into this function, that's also the height of the function. So you're kind of getting, the reason this divides out to 1 is because if you're getting close to 0, the sine of something close to 0 is close to 0, and then you're plugging in that same height, that same y value, so it divides out to 1. All right, number 69. Now, this is not just equal to 1 necessarily because we have a sign squared here, but we can kind of unsimplify this. This is the limit as x approaches 0 of, instead of sine squared x, let's write that as sine x times sine x. That's equivalent to sine squared. And then the divided by x, that would just be divided, like one of these is just divided by x. It's not divided by x because we don't have an x squared down there. So now if I have a product in here, again, we talked about limit properties. I can take the limit of each piece of the product. I can take the limit as x approaches 0 of sine x over x, and I can multiply that by the limit as x approaches 0 of sine x. So this first limit is 1, and then the limit as x approaches 0 of sine x is sine 0, and we're thinking back to our unit circle trig days. So sine of 0, what's the y coordinate at 0 radians? It's equal to 0 as well. So 0 times 1 is 0. All right, for number 71, this was the second trig limit that we talked about in our notes, talked about memorizing this as well. So without the squared piece, the limit of 1 minus cosine x over x as h approaches 0 is 0. So I can kind of separate this out like I did on the last one. I don't want to FOIL this out, but I do want to just separate it. So I've got 1 minus cosine h over h, and then multiplied by another 1 minus cosine h. So I'm just taking the squared out and kind of expanding it. And then similarly, I can say if I'm taking the limit of a product, I can take the limit of the individual pieces and then multiply those limits together. To be honest, for our AP test, you're probably not going to be showing all of this work. I'm getting kind of detailed with how I'm showing it, but you do need to be able to perform the work, maybe do it in multiple choice. So this first limit is 0. The second limit doesn't really matter because I'm going to multiply it by 0, but it's 1 minus the cosine of 0. Cosine of 0 is 1. So 0 times 0 is 0. For 73, again, we get 0 over 0. That's an indeterminate form, so we've got to work on this a little bit. So this is the limit as x approaches pi over 2. And then we're going to rewrite this so it's cosine x. Instead of dividing by cotangent, which is cosine x over sine x, we can multiply by the reciprocal of cotangent. So multiply by sine x over cosine x. And then the cosine x's cancel. So now it's just the limit as x approaches pi over 2 of sine x, and that is sine of pi over 2. We're at the top of the unit circle thinking about the y coordinate. Sine is equal to 1 at pi over 2. All right, back in our pre-calc days, we did something like number 85. We often used h, but remember, this is the difference quotient here. The difference quotient represents a secant slope. And if you're taking the limit as delta x, which is the space between the 2 points of your secant line, if you're taking that limit of a secant slope, what you're going to achieve is a tangent slope. So I am going to do the difference quotient on number 85, but you might remember this, again, from our pre-calc days. If I say f of x is something linear, and I say find the formula for the slope of any secant line or the slope of any tangent line in this case, you should just look at the slope and say it's going to be 3. And we'll talk more about that when we get closer to chapter 2. But otherwise, I don't want to write equals here. Otherwise, if I do this work, f of x plus delta x means plug that expression in for this x. So 3 times x plus delta x minus 2. And then I'm going to work on this limit. So limit as delta x approaches 0. So f of x plus delta x is, let's distribute 3x plus 3 delta x minus 2. And then subtract f of x. So subtract all of f of x, meaning subtract with a quantity or distribute the negative through. And then this whole thing is over delta x. So I've got to work on this until I can get that delta x to cancel out of the denominator. And all kinds of stuff cancels out. So if you distribute this negative, Then this 3x will cancel with this negative 3x. Minus 2 will cancel with plus 2. So all that we're left with is the limit as delta x approaches 0 of 3 delta x over delta x. That the delta x's can divide out. So now it's the limit as delta x approaches 0 of just a constant, and that is equal to 3. So, like I said, if the function is linear, then this expression, which represents the slope of a tangent line, should just come out to the slope of the original function anyway. If f of x is anything other than linear, then you're going to get an expression. It won't just be a number. So for example, 86, we're doing the same thing, but f of x is square root of x. So on a square root curve, depending on which point of tangency you're looking at, the slope's going to change. So we should still have an x in our answer here. So I'm going to start right off with the limit expression here. So f of x plus delta x. So in this function, that'll just be square root of x plus delta x minus f of x, which is square root of x, all over delta x. We can't plug in 0 right now for delta x because we would get 0 divided by 0, which is an indeterminate form, meaning we've got to do more stuff to it to figure out the limit. And so we multiply by the conjugate of the numerator. So the conjugate of the numerator is the square root of x plus delta x plus, that makes it a conjugate, square root of x. And this is legal as long as you multiply on the top and the bottom. And that's because what you're really doing is just multiplying by 1, so you're not changing the value of anything. This is just a very specific version of 1 that we need to make the problem work. All right, so keep your limit notation until you actually do direct substitution. So when we multiply conjugates together, remember you can really just multiply first times first. So this becomes x plus delta x, and last times last, so minus x. And then in the denominator, I'm not actually going to distribute this through. I'm just going to write delta x times the quantity, square root of x plus delta x plus square root of x. So in the numerator, x minus x adds up to 0, cancels out. And then also this delta x and this delta x, they will divide out to 1. So now we're just left with the limit as delta x approaches 0 of 1 over just square root of x plus delta x plus square root of x. At this point, I can try direct substitution again. So if I put in 0 for this one little delta x, I get 1 over square root of x plus square root of x. And we can combine those like terms. So that's 1 over 2 square root of x. All right, number 89 says use the squeeze theorem to find the limit as x approaches c of f of x. So in 89, c is 0. That's the value we're approaching. And f of x has been squeezed between two parabolas, 4 minus x squared and 4 plus x squared. So if I want to use the squeeze theorem, all I have to do is take the limit as x approaches 0 instead of c of each piece of this inequality. So take that limit of 4 minus x squared. That limit has to be less than or equal to the limit as x approaches 0 of f of x. And that has to be less than or equal to the limit as x approaches 0 of 4 plus x squared. So I've just taken the limit of each piece, assuming this inequality is true. And then I can use direct substitution for the first limit. So 4 minus 0 is 4. So 4 has to be less than or equal to the limit as x approaches 0 of f of x. And that has to be less than or equal to 4 plus 0 squared, so 4 again. So this is called the squeeze theorem because you're saying this limit has to fall between 4 and 4. So the only possibility is that the limit as x approaches 0 of f of x, it has to equal 4. If it's got to squeeze between 4 and 4, the only option is for it to be exactly 4. All right, and this last one says use a graphing utility to graph the given functions, absolute value x, negative absolute value x, and the graph of number 91, which is x cosine x. And then again, we're going to use the graphs to observe the squeeze theorem visually. We want to find the limit as x approaches 0. So I've done that here. If you need, let's see, I can do that quick crash course on this. Absolute value is either math over to number right here, or it's one of these alpha menus. I think it's alpha window. Yeah, alpha window gets you a nice set of shortcuts as well. So either way. All right, so absolute value of x, and then negative absolute value of x. And problem number 91 was x cosine of x. Also, make sure that you're in radian mode and not degree mode, especially if you are also in physics this year. All right, and then I'm just going to do a standard viewing window. So I always do zoom 6, gives me a 10 by 10 grid. So that's where this graph came from. So I screenshotted that here. And then again, we're just saying, yeah, I can see that this x cosine x graph falls between the two absolute value curves. And so we're kind of doing the same thing by saying that the limit, I'm not going to show all the inequality notation because we're just visualizing here, but the limit as x approaches 0 of x cosine x is definitely just equal to 0. I can see that it's getting squeezed down to 0 right here. So I didn't really show a bunch of work for that. I could set up something similar, an expression like this, but it just said to do things visually. So I'll just stop there with that.